Now that maintenance might be electrical maintenance or mechanical maintenance. Both are different, right? So let's suppose you are giving this for mechanical maintenance. Now, when any worker is performing maintenance activity on your pump, you need to ensure that there should be no possibility of electricity or current during that maintenance activity. So what the procedure will be followed, that first of all, now in this case, how many permit will be issued, if anybody can answer? I am giving my pump for mechanical maintenance. Now, how many permit will be issued? I told you that there should be no possibility of electric current or electricity during the maintenance work. So to carry out this work of maintenance of the pump, how many permits should be there? How many permits should be issued? Now, if I am asking, uh, now let me tell you that there will be two permits, right? Now, which two permits will be there? If anybody can answer.
Hello, sir.
Yeah.
Sir, till the participants are giving the answer, sir, I would like to remind them that at the end of the session, we are having the quiz.
Yeah.
So the link for the same will be shared in the chat box of this meeting only.
Okay. How many permits for at least give? I told you, equipment opening. No, you are just pump is not kind of equipment, because pump is your machine. Equipment in plant you will consider either the column or vessel, right? That might be distillation column, absorption column, stripper, reactor, any feed surge vessel, right? All this will come under equipment. So this pump and all these are machinery. So in that you don't have to issue equipment opening permit. Yeah, one will be cold work permit. Cold work permit is for maintenance work, and another. Yesterday I show you that in India we issue four types of permit. That is cold work, hot work, confined space, and electrical isolation. So for maintenance of this pump, you will require two permits. One will be your cold work permit for maintenance work. Another will be electrical isolation permit. So what will be if you are in charge of the plant, right? And if permit is come to you, this cold work permit is come to you for that you have to give the pump for the maintenance. What will you check first? What will you check first? Will you immediately sign the cold work permit? Let me give you some brief. Let me give you some brief scenario that you have already isolated and everything is done, right? It inlet and outlet valve and everything is shut off. Your pump is ready to go for the maintenance. Okay, worker can come and he or she can start the maintenance activity. But before issuing the permit, what will you check? Because when the permit will come to you, only one permit will come to you or two permit will come to you. I am asking that your pump is ready for maintenance. Your pump is ready for maintenance. It means that I have already shut off my inlet outlet valve. I have drained it. Everything I have done. Right. Immediately my pump is ready for the maintenance. And I have already told you that when the pump is going for the maintenance activity, there will be two permits. That is, one will be cold permit, another will be electrical isolation permit. Electrical isolation permit means there should be no chance or no possibility of electric current during this maintenance activity, right? So whenever a worker will come with a permit to get a sign of yours, because you are the in charge of plant, worker is coming to you, and he or she will tell you that please sign the permit. So will you, and your authority, because you are not from electrical department, right? So your authority will be on cold work permit only. Correct. So you will sign the cold work permit. But before signing cold work permit, what will you check? Okay, lockout and tag out. But okay, you are like 50% answer is there. But like, will you do without any checking of means if you are locking the pump, will you do without checking anything? What will you check before putting lock? Let me give you the answer. You need to check whether electrical isolation permit is signed or not. Because the meaning of electrical isolation permit means from the electrical department, from the electrical substation, they have cut off the power for that particular pump. In the electrical substation, there will be a separate switch, or say there will be a separate switch and everything for each electrical equipment. That is, if your pump, compressor, whatever the thing is there, for each and every equipment there will be a separate switch. So electrical isolation means electrical department will shut off the or cut off the power of that particular pump. So you need to check that whether electrical department has signed that permit or not, whether they have isolated this pump or not. Now when that now if it is confirmed that the pump is electrically isolated, lock means there will be a push button to start and shut off the pump. There will be a kind of red button, that is push button. You just need to start, if you want to start, you just need to press the button. Right? So just to prevent starting or shut off, the push button, you need to clip that. You need to put one clip over there. And on that, you will put one red tag. You will put one red tag. And on that red tag, you will mention that pump is under the maintenance. And don't start the pump until the further instruction. Let me just take. So it will be like this. Can you see this screen?
Yes, sir, it is visible.
Yeah. So here it is written. Usually this lock, they don't put this lock usually. This might be like performed in foreign countries, but in India, usually this lock they do not put. Usually they just put this tag only, right? And on that, the person here it is written name, right? So you will put your name here, and why it is locked you will mention, and you can mention the permit number or something like that. Okay, and that's how this is the example of lock. That is lockout. You have locked the system. And now, whenever you will remove the tag, once the cold work permit is closed, right? Once the cold work permit is closed means the maintenance work is done. You have checked everything, and then you have to close the permit. Opening of the permit means you will put the time, you will sign that, okay, so you will put the time again that at the 11 a.m. work is completed, and you will sign the permit. And after that, you will inform to electrical department, right? And before that, you will remove that tag which was locked. You will remove that tag. That is known as tag out. Okay, that is lockout and tag out. You will remove the tag. You will inform to electrical department that you can start the supply of power or supply of electricity to the pump. And when they will supply the electricity or they will start the power, you need to check by you need to check whether the pump is running or not, right? So that is the full procedure when you want to give the pump in the for this maintenance job. Correct? So I think lockout tagout is clear now. A lockout tagout is part of this whenever you are giving it usually used for electrical equipment, lockout and tagout, right? So pump, compressor, which are running through electricity, right? Because compressors are steam turbine based also, right? There will be steam driven compressor and there will be electrical driven compressor. So the lockout and tagout will, when it is maintenance for electrical driven, electricity driven compressor, then there will be a lockout and tagout for that compressor also. Correct? So whenever electricity is involved, you will use this lockout and tagout. Okay. Now the first video of the day we will see, and that is and again I am telling, don't be afraid. There might be like some people might be sensitive, and after watching this they might get afraid, but there is no like, don't get afraid. It was just a kind of we will discuss that what was happened and everything, right? Permit is used. Equipment opening permit is usually equipment opening permit is not used in India, but in foreign countries, like equipment permit is for this equipment, like yesterday I told you about that feed surge drum cleaning, right, where we were issuing confined space entry permit. Correct. So before your equipment is, we have shut down the plant. We have shut down the plant, and you have already removed the liquid from that particular vessel. Correct. But still you don't want to take a chance. That's why there will be a permit of equipment opening, that you are opening this particular vessel. If it is reactor in which catalyst is loaded, if it is the reactor in which catalyst is loaded, you want to remove the catalyst. And now, if you are you want to remove the catalyst only, there is no need of this confined space entry, right? Because person is not going to enter into the reactor, correct? Because the catalyst from the reactor will be removed using vacuum or say ejector, vacuum ejector. Right, by using vacuum, you can remove the catalyst. So it means that to pull out the catalyst, somewhere or the other side, you have to open one of the portion or one of the nozzle of that reactor. So that will come under equipment opening. Right. In India, usually we don't give equipment opening, but in Middle East and foreign countries, there might be a separate permit for this equipment opening. Because like in India, usually whenever there is a shutdown, then only people used to open the equipment. And if there is emergency, then also there will be an emergency shutdown. If something has in sulfur recovery unit, in reactors, catalysts are loaded. And if something is happened to sulfur recovery unit, so only not whole refinery, but only sulfur recovery unit will go under the shutdown. And talking about petrochemical plants, in petrochemical plants, the first equipment will be cracker, naphtha cracker. Right, in petrochemical plant, there will be a cracker. And in cracker, there will be a catalyst of, the catalyst will be loaded inside the tubes. Right. So every 2 or 3 months, the pigging will be done. What the meaning of pigging means? You will enter a rubber cork. Somewhat big rubber cork will be there. You will enter that rubber cork inside the pipe, and by pressing it via water, right? By pressing it via water, you will remove entire the coke formation or catalyst. You will remove from the pipe. That is known as pigging activity. For that, you are opening the cracker. So for that particular scenario, you will use the equipment opening permit. Right. So that is, I think, is it clear to you now that where the equipment opening permit will be there? So what I was telling that the whatever we will see that please don't worry and don't get afraid. Like it's a very normal things, and don't these are the past events. Okay, nowadays people are taking care of everything, and there are they try to avoid such accidents and all. The safety measures are very stricter. The safety measures are very stricter in every part of the world. So don't worry about that. And if you want to work in the plant, don't change your decision that okay, this kind of things might happen. Because I know that whenever I was about to take admission in chemical engineering, entire family and friends all were telling that whenever you are taking admission into chemical engineering, your life will be reduced to half. For that reaction, we use half-life equation, right? So if I was about to live, say, 80 years, so my lifespan will be now 40 years only. That people used to tell. And that's how my parents and all were like, okay, don't send him to chemical engineering stream. But nothing like that. Everything is perfect, and like it is a very good branch to work in. And even if you are interested in working in production, because whoever is going to work in the production department and process department, they are going to directly work into this petrochemical plant. If you are going to work in the designing industry, then there will be a separate department, right? But if you are working in process department or in production department, then you have to work inside the petrochemical plant or say petroleum refinery. Correct. So everything is very smooth and okay in present scenario. So don't worry and don't get afraid, right? We will start our day first video, and it is Piper Alpha. Is it visible? Hello.
Yes, sir, it is visible.
Yeah, okay. And sound is also coming, right?
Yes, sir.
Now in this Piper Alpha, yesterday we have discussed about work permit system, right? So please closely look this video. What was happened, we can see the video once again also if you don't understand. But see, because whatever we have discussed till now, you will see that what will happen if you are bypassing the yesterday we have seen the life saving rule at the end. So you will see that if you are bypassing even any one of the life rule, there is then the possibility of accident and event starts from there. Whenever you think or whenever you start the bypassing of these rules, right? So in this also there will be something like that, and you will figure out that. So just watch.
The Occidental Petroleum Corporation is an American oil and gas exploration and production company based in Texas. Founded in 1920, it has a global profile with worldwide operations. Occidental discovered the Piper Alpha oil field in 1973 and built the platform which became operational in 1976. The rig was home to 200 crew who lived and worked on the platform for months at a time. The platform stood more than 470 feet above the water and was situated around 120 miles northeast of the Scottish city of Aberdeen. The modular designed platform consisted of 4 main operating areas, which were separated by firewalls designed to withstand oil fires in an arrangement which ensured hazardous operating areas were located far from personnel and command areas. At its peak, Piper produced 300,000 barrels of crude oil daily, 10% of the UK's consumption. In addition to the 128,000-mile pipeline connecting Piper Alpha to the Flotter oil terminal on the Orkney Islands, Piper's operations included the extraction of the gases methane, propane and pentane, which required gas pipelines that connected it to the Claymore platform, Tartan platform and the separate MCP-01 gas processing platform. The Piper Alpha had 1 export riser and 3 gas risers to facilitate the safe transportation of the oil and gas from the seafloor to the platform. To enable the Piper Alpha to process gas, essential works were carried out. Major modifications to the rig became necessary, and some of the original safety measures were compromised. These included the installation of a gas conservation module, GCM, and alterations to Module C to enable gas processing. This change of use from oil to gas was completed in 1980, and the Piper Alpha started processing gas via the gas conservation module. In 1988, this module required maintenance, and operations reverted to processing gas with the compressors located in Module C. At 12 noon on July 6, 1988, an engineer performing routine maintenance removed the pressure safety valve from pump A, one of the 2 Piper Alpha condensate pumps located in Module C. He then used a hand-tightened blind flange to seal the pipe and completed a permit stating that pump A should not be switched on. At 6 p.m., shifts changed and the night crew assumed duty. At around 9:45 p.m., pump B became blocked with methane clathrate icy condensation. As the entire power supply of the offshore construction work depended on this pump, the manager had only a few minutes to bring the pump back online, otherwise the power supply would fail completely. The night shift were aware that a permit was in place for pump A, but they were not aware that the relief valve had been removed for maintenance under another permit. They went on to restore the power supplies, open the suction lines, and at 9:55 p.m. pump A was switched on. The hand-tightened blind flange failed. A large amount of condensate was released, which created an explosive vapor cloud, resulting in a chain reaction of explosions and failures across Piper Alpha. Firewalls, which were designed to withstand burning oil, crumbled under the pressure from the detonating gas. The fire spread through the broken firewalls, fueled by the tartan and Claymore's continued gas production. At 10:04 p.m., the control room was abandoned and Mayday was signaled. At 10:20, the tartan gas line ruptured, releasing 15 to 30 tons of pressurized gas every second, which ignited. Shortly after, the Claymore and the PCP-01 gas lines also ruptured. Thick black smoke made helicopter rescue virtually impossible, and lifeboats could not be reached. The disaster resulted in the tragic deaths of 167 workers, damages costing £3.4 billion, and substantial damage to the environment. Judge William Cullen's inquiry found the primary cause was an unsafe permit-to-work system. But unlike other disasters before and since, the inquiry also revealed widespread and serious safety failures, not only in Piper Alpha's systems, but in Occidental's management and the Department of Energy's regulation of the industry. The permit system failure appears to be the initiating event, but it should not have been possible for a procedure failure to have resulted in such an accident. The disaster was a confluence of design flaws, human error, and bad luck, including failure of the permit-to-work system, no formal handover between shifts, safety policies and procedures not followed, no drills or exercises to test emergency response, no training for disaster management, failure to conduct adequate risk assessments. Of the 226 crew on board Piper Alpha on that fatal day, only 61 survived. Although the Lord Cullen inquiry attributed the blame to Occidental, no criminal charges were brought. The company was heavily criticized by the Health and Safety Executive and media. The inquiry resulted in 106 recommendations for changes to North Sea safety procedures, all of which were accepted by the industry. The most significant recommendation was for the Health and Safety Executive to bear responsibility for North Sea safety, replacing the UK's Department of Energy. This removed the conflict of interest for one organisation to oversee production and safety. The Piper Alpha disaster was the catalyst for the UK development of safety case requirements. An evidence-driven approach, validating safety measures' effectiveness, ensuring risks are minimised. The Piper Alpha disaster was the largest man-made disaster at the time, and it continues to be the worst offshore disaster in terms of lives lost and impact on the industry. In the space of 2 hours, the Piper Alpha was reduced to a shell. In the 10 years that followed the disaster, the offshore industry spent more than £2 billion on health and safety. The Piper Alpha disaster in 1988 shocked the world and had a global impact on the safety culture, safety management, and legislation across all industries.
So, quickly tell me, what was the major contributing factor? Which was the major contributing factor? All I believe that all of you understood what happened, right? Because my first question should be that. Okay. Yeah, so all of you understood that is first requirement. Questions will be followed after that. So permit issued was, I think, right, but first of all, the work after permit, that a flange, PSV which was removed, so the flange were not tightened, right? So they need to, if you are the in charge of the plant, right? You need to check that whether they have everything is in proper fashion or not. Yesterday or on day one, someone has pointed about that positive isolation, right? So if I don't know whether you have heard or not, but there will be a blind, right? Blinding procedure. We usually use this term blinding of the line. So if you are blinding a flange, you will put one disc type object between two lines, and all the time, whenever there will be, if you are opening the pipe, or say if you are opening the flange, keep in mind that every time you need to use fresh and new gasket only, right? Because there are so many incidents due to this gasket failure also. Gasket, you know, right? You must have studied during your academics that gaskets. So gaskets are installed to prevent leak. So if you are putting a blind will be a kind of disc, right? There are so many blinds are available, that is a spectacle blind, or say what you say, spad blind. So let me just show you. Can you see the screen?
Yes, sir.
Yeah. So this is spectacle blind, right? Whenever you will, whenever you are putting up, if you want to blind that pipeline, means you don't want to pass flow through that, right? At that time, you will put this part inside. And whenever your pipeline is in running condition, that is fluid is passing through that, you will put this part inside. So on this side and on below that side, on both the side, fresh and new gaskets should be used, right? So what happened at Piper Alpha, that this flange tightening was not proper. First thing was that they have not, for their condition, this type of flange should be used, because it was open flange. So on bottom of the flange, you need to use this. On above flange, you need to use this, right? But they haven't used this kind of any kind of this blind, and if even it was used, it was not tightened, right? And if tighten and all that are different things, the person who was in charge has not checked it properly, right? Whether the worker has performed the work effectively or not. Above that, charge handing over was not proper. That when the shift changes, that's, let's suppose I am working in morning shift, and if I will leave the plant in second shift, that is in afternoon shift. So whenever my colleague is coming, I need to tell him properly whatever I have done in the morning shift, each and everything. If I have taken the sample, I need to tell him. If I have set up the plant, I need to tell him. If even I am closing the bypass, I need to tell him. Whatever you do in your shift, you need to tell everything related to plant. Right? Whatever you do related to plant, you need to tell each and everything to your colleague. So this procedure was not proper for this Piper alpha case. And what happened that they started pump A, which was not supposed to start, it, right? Because it was already under maintenance. And the person who started it was not knowing this because charge handling was not proper. Correct? And that's how whole incident happened. So what we learned from Piper alpha case, that permit system should be proper. You need to check the work, what is execution of work should be proper. It is your duty because you are the in charge of the plant. So it is your duty to check whether blinding and everything is perfect or not. And the third thing, charge handover should be proper. Each and everything should be, there is a record book. So you need to write each and everything. You need to hand over that because sometimes you forget to mention during verbal discussion. But the person who is coming in the next shift, he or she should not depend only on the verbal discussion. He should refer that written record also. So if it is missed in the verbal discussion, you will find everything in written record also. And in written record also, it is my suggestion to all of you that if you are going to work in the plant, please write everything immediately after the work is done. Because usually what we do, that we write everything at, like if my shift is ending at 2 p.m., I will write everything at 1:30 p.m. Don't do this. Because if you will write everything at the end of the shift, there might be chances of missing something. So whenever you are executing or performing some task, immediately write there that I have performed this, I have done this, so that at least your written record should be perfect. If you can miss something in verbal communication, you can, the person who is coming in the next shift, he or she can always refer your written record and he can see that what he or she can see that what was happened in the first shift. Right. So that was all from the Piper alpha. Now we will quickly move to second incident, that is Texas City. And
The U.S. Chemical Safety Board is developing a new interactive training application focused on OSHA's Process Safety Management, or PSM, regulation. The training will cover the 14 elements of PSM using the 2005 explosion at BP's Texas City refinery as a model. Look for it soon at csb.gov. March 23rd, 2005. The BP refinery in
video
Texas
is
City,
visible and
Texas.
audible, right?
Several units at the refinery had been shut down for lengthy maintenance projects, which required nearly 1,000 contractors to be on site, along with BP employees. BP had positioned a number of portable trailers close to process units for the use of contractors and other maintenance workers. Over a period of months, BP had located 10 trailers for workers servicing the ultra cracker unit including a double-wide wood-framed trailer that contained 11 offices and was regularly used for meetings. Though these trailers were located near the isomerization unit, the occupants were not warned the ISOM unit was about to start up, a potentially hazardous operation. At 2:15 a.m. on March 23rd, overnight operators began introducing flammable liquid hydrocarbons, known as raffinate, into a 170-foot-tall raffinate splitter tower used to distill and separate gasoline components. Near the base of the tower, there was a single instrument that measured how much liquid was inside. It transmitted this information to both a satellite control room and a central control room located away from the ISOM unit. But this level indicator was not designed to measure liquid above the 9-foot mark. During normal operation, the tower was only supposed to contain about 6½ feet of liquid. But during startups, operators routinely deviated from written procedures and filled the tower above the 9-foot mark, concerned that if the liquid level fluctuated too low, it would cause costly damage to the furnace. At 3:09 a.m., as the liquid neared the 8-foot mark, a high-level alarm activated and sounded in the control rooms. But a second high-level alarm, slightly further up the tower, failed to go off. By 3:30 a.m., the level indicator showed that liquid had filled the bottom 9 feet of the tower, and the feed was stopped. The CSB later estimated that the liquid was, in fact, at a height of 13 feet, but operators could not know the actual level because the indicator only measured up to 9 feet. The lead operator had been overseeing the startup from a satellite control room within the ISOM unit. At 5 a.m., he briefly updated the night board operator in the central control room about the startup activities. The lead operator then left the refinery early, an hour before the end of the shift. A new board operator arrived in the control room around 6 a.m. to start his 30th day in a row working a 12-hour shift. He spoke briefly with the departing night shift operator and then read the logbook to prepare for the startup. But the logbook did not clearly indicate how much liquid was already in the tower and equipment, and it left no instructions on routing of the liquid feed and products when the startup resumed. Instead, the control board operator only found a one-line logbook entry that said ISOM brought in some RAF to unit to pack RAF with. At 7:15 a.m., the day shift supervisor arrived. Because he was more than an hour late, he received no formal briefing from personnel on the night shift about conditions in the ISOM unit. At 9:51 a.m., operators resumed the startup. They began recirculating the liquid feed and adding more liquid to the already overfilled tower. As new feed was added, startup procedures called for regulating the liquid level in the tower using the automatic level control valve. But the board operator and others had received conflicting instructions on routing the product. As a result, this critical valve was left closed for several hours, blocking the flow of liquid from the tower. A few minutes later, operators lit burners on the furnace to begin heating up the feed, part of the normal startup process. While the startup was underway, the day supervisor left the refinery on short notice, just before 11 a.m., to attend to a family medical emergency. Contrary to BP's own procedures, no experienced supervisor was assigned to replace him. This left a single control board operator, now without a qualified supervisor, to run 3 refinery units, including the ISOM unit, which needed close attention. The refinery had eliminated a second board operator position following corporate budget cuts in 1999 after BP acquired Amoco. As the startup continued, the tower steadily filled with liquid, reaching a height of 98 feet shortly before noon, more than 15 times the normal level. But the improperly calibrated level indicator told operators in the control room that the liquid was at 8.4 feet and gradually falling. Furthermore, the control panel was not configured to clearly warn operators of the growing danger. It did not display flows into and out of the tower on the same screen, nor did it calculate the total liquid in the tower. Meanwhile, the maintenance contractors, who were not involved in the operation of the ISOM unit, left their work trailers to attend a company lunch, celebrating a month without a lost time injury. At 12:41 p.m., an alarm activated as the rising liquid compressed the gases remaining in the top of the tower. Unable to understand the source of the high pressure, operators opened a manual chain valve to vent gases to the unit's emergency relief system, a 1950s-era blowdown drum that vented vapor directly into the atmosphere. Operators also turned off 2 burners in the furnace to lower the temperature inside the tower, believing this would reduce the pressure. Nobody knew the tower was dangerously full. The operators did become concerned about the lack of flow out of the tower and began opening the valve to send liquid from the bottom of the tower to storage tanks. But this liquid was very hot. As it flowed through the heat exchanger, it suddenly raised the temperature of the liquid entering high up the tower by 141 degrees Fahrenheit. It was now about 1 p.m. Contract workers, unaware of the startup and the looming danger, returned from lunch and began a meeting in the double-wide trailer, in the corner room closest to the blowdown drum. Over the next few minutes, the hot feed entering the tower caused the liquid inside to start to boil and swell. Liquid filled the tower completely and began spilling into the overhead vapor line, exerting great pressure on the emergency relief valves 150 feet below. At 1:14 p.m., the 3 emergency valves opened, sending nearly 52,000 gallons of flammable liquid to the blowdown drum at the other end of the ISOM unit. Liquid rose inside the blowdown drum and overflowed into a process sewer, setting off alarms in the control room. But the high-level alarm on the blowdown drum failed to go off. None of the operators knew of the catastrophe unfolding in the ISOM unit. As flammable hydrocarbons overfilled the blowdown drum, operators nearby saw a geyser of liquid and vapor erupt from the top of the stack. The equivalent of nearly a tanker truck full of hot gasoline fell to the ground and began forming a huge flammable vapor cloud. The vapor cloud expanded in just 90 seconds, engulfing the unit and the nearby trailers full of workers. About 25 feet from the base of the blowdown drum, 2 workers were parked in a pickup truck with the engine idling. As flammable vapor entered the air intake, the diesel engine began to race. The 2 workers fled, unable to shut off the engine. Moments later, witnesses saw the truck backfire and ignite the vapor cloud. Powerful explosions swept through the area. The blast pressure wave accelerated through the ISOM unit, causing heavy destruction and igniting fires. The workers inside the trailers were right in the path of the explosions. The fires continued to burn for hours. 12 of the 20 occupants of the double-wide trailer were killed, along with 3 workers in a trailer nearby. 180 workers were injured, many with serious burns, fractures, or other traumatic injuries. The wood and metal frame trailers were blown apart by the blasts. Firefighters struggled to rescue the injured and recover the victims. 50 large chemical storage tanks were damaged, and the ISOM unit remained shut down for more than 2 years. The disaster at BP Texas City was the most serious refinery accident ever investigated by the CSB.
So volume was not that much proper.
No, sir, it was okay. It was fine.
Sorry.
Sir, it was proper, no issue.
Yeah. So What is the learning from this Texas city? This was quite like more disastrous than Piper Alpha, but yeah, this kind of things happen when you bypass like normal working hours and whatever the procedure. You can see that they have assigned everything to non-experienced person, right? Now, uh, if you are not confident for anything, if you will tomorrow you will go to the plant, and if you are not confident for anything, please, it is your right to say no. It won't affect anything about your job. You can tell them, because I am not experienced, please give me first the demo, right? Without that, there on day one only, I told that you are surrounded by bomb. What was happening that? Because the fire happened, and then in last also they have mentioned that so many storage tanks were damaged and everything, right? So the fault in this thing, for very first fault was that liquid level system, right? Usually in automation or in industry, they usually put uh, uh, say there will be emergency, or say there will be a shutdown on some level controlling, right? That whatever this was the tower, but usually if it is a small tank, a storage tank, or the drum which was say blow down drum, usually in all that at 50% level, there will be a shutdown or emergency shutdown of that particular equipment. No further liquid can come inside that, right? And you need to immediately drain the drum. So there will be a 2 to 3 level controller will be there. You have seen that in that there was alarm at first instant, right? High alarm. It is known as high alarm, low alarm. That will be that kind of controllers will be installed. So if the level will be above 50%, your equipment will be your shutdown. It will give you alarm at say 15%, 25%, right? Usually it around 15, like if it is 15%, you need to maintain, then the alarm will be at 30%, 40%, right? Above that, you can't feel the drum further. And from that level indicator only this whole scenario started. And other contributing factors were, yesterday I told about that vehicle fitness also, and the spark arrestor. I used one term, that is spark arrestor. In this scenario also you have seen that the source of fire was that spark from that vehicle, right? If the silencer of that vehicle would have installed that spark arrestor, this wouldn't have happened, right? So collectively there were so many problems. First of this level indicator, inexperienced operator, vehicle without spark arrestor which was parked in the plant area, right? Apart from that, if we consider the fatalities, because the porta cabin was very near, it is obviously it is job of civil department that where the porta cabin should be, but usually there should be a safe distance from your plant area. Porta cabin should always be at the safe distance at the plant area. In Reliance only, crane fell down on the porta cabin, and around 4 or 5 people were there and they died immediately. Reliance Industries Jamnagar. Crane fell down on the porta cabin. So it is the duty of this like management, where to place these porta cabins. It should always be at some nearby distance, or say it will always be nearby distance to, or say, assembly point or the safe area, because we have seen that assembly point is the safest area nearby the plant. So your porta cabin should also be at those kind of distance only, right? So you need to take care of these things while working in the plant. Okay, and I will share one name of the book which you should refer. That is this. In that it is given the summary of these incidents, like here is that the whole summary of that is there. नो आप सेफ्टी अलार्म्स को कंट्रोल रूम नहीं, पॉइंट ही वहाँ पे जो लेवल इंडिकेटर था उनका, इट वाज लाइक फिजिकल लेवल इंडिकेटर also, and the controller will be at your control panel only. You can't install that in different department, but what you can do is you can use multiple controllers. Right, because in SR there were usually 3 controllers for every equipment. If one fails, your 2 are still working. If 2 fails, your 1 is also still working. So you can install multiple controllers, but you can't install control at other department. The name of this book is have you guys have heard about this library Genesis? This is the book. You guys can take a screenshot, and if you will search this on library Genesis, the website looks like this. Right. You please search for this and just put Trevor Clays in that. Trevor Clays is the guy who dedicated his entire life for these safety things only, and he has written multiple books on the safety. Yeah. So here the book which I have shown to you, it is this book, compendium. Then his other book is this What Went Wrong. You should refer this book also. You guys
Can you please share the link of the book in chat box? Just copy and paste it, then it will be easy for them to access.
Okay. No, I thought guys must be knowing this, that's why. Yeah. But in last incident, the in charge of control room may be deviated in paperwork. That's why I'm talking. No, but like there will be alarm, right? Whenever some abnormal things will happen, there will be alarm. So even if he was deviated in paperwork, if alarm sound is there, and even alarms will have a tag number. It is like it is kind of so many things you need to memorize. Whenever you are working on a control panel or in DCS panel, so many things you need to remember. So whenever alarm start to like if alarm is there, by reading a tag number, you should be able to tell that which equipment's tag is this. Right. So even if he was deviated in paperwork, whenever the alarm was there, he should be able to tell that okay, this is for my level of tower. So we can't install control in other departments. It is because the company has hired that person to do the work in control panel only. So you can always use multiple controllers and another thing. What in that it was mentioned that only one person was looking after 3 units. This is very ridiculous scenario.
Sir,
Yeah.
sorry, but this link for what? Examination or
Sorry.
for what this link you sent in chat box?
I have sent you.
What is this? I
This
don't
book
understand.
is this is the link for the book that you should refer for in know about the for knowing about the safety aspects, right, sir?
Okay. Now I understand. And how about quiz?
Please, the session to be continued. Quiz will be conducted at the end only.
Okay. Thank you very much.
So
Please continue, sir.
yeah, no issue. So you can always like it is that person starts to do the work properly, and but I like company at that time one plant was on startup, right? If in Reliance or SR or IOCL, if plant is under startup, only the guys which are of production, they will be in the plant. શું કરે છે અહીં કેમેરો ચાલુ so those person who are working in production they only they will work inside the plant, right? All of the people, upper management and these control room people, all will be on the this control system or say on control panel. Because during the startup of plant, even they are like upper management or say boss of the plant, head of the plant should be there. Here, non-experienced person was there for startup of the plant, right? Which is not acceptable. And he is also looking after 2 more plants. In SR for FCCU plant, there were 3 people for this control system or on DCS panel. For ISOM also, we have seen this for ISOM, right? For the ISOM also, there will be 2 persons. Like even if one person is going for a washroom or some lunch, dinner, one person should always be there on control panel. Right. So that was the and it was even mentioned also that when BP acquired Amoco, they have started reducing the budget, right? So they haven't hired enough people. Staff was not enough, right? The plant was very understaffed. So that was not good, right? So these many factors were there. Okay, so now we will see Chernobyl.
Nuclear power had
Volume is perfect,
become
right?
routine, and a bright atomic future lay ahead.
Yes, sir, but if possible, then raise the volume.
Of
Yeah,
these
yeah,
huge
okay.
power stations. But there is only one of these we all know about, Chernobyl. On this evening, there was no hint of the catastrophe about to unfold that would have a profound impact on the USSR and
Now it
nuclear
is
power
perfect.
around the world. At 1:23
Yes,
a.m.
yes.
during a safety test, the AZ-5 button was pushed. About 8 seconds later, reactor 4 exploded. Why did the emergency shutdown blow up the reactor? This is the central Chernobyl question. At the time of the disaster, Ukraine was one of the 15 Soviet republics. Chernobyl was in northern Ukraine, near the Belarus border. The centerpiece of these power stations was the RBMK reactor. The RBMK was a graphite reactor which had been powering Soviet growth since 1970. Chernobyl's reactor number 4 was only 2.5 years old. These are the main systems of the RBMK design. The nuclear reactor produces large quantities of heat. To collect this heat, pumps circulate water in pipes vertically up through the reactor. Steam is collected in separator drums. The steam spins the turbine generators which power the electrical grid. The steam is cooled back into water from a large lake and fed back into the main circuit, and the cycle repeats. It runs like this at full power for months on end. The buildings required to accommodate the systems were extensive. The components were located inside individual concrete compartments. The concrete vault around the reactor was 2.5 meters thick. The reactor was housed inside a steel drum. A central component of this story is graphite. Chernobyl's RBMK core contained huge amounts of it, which was essential for the nuclear reaction. When an atom splits, it releases neutrons at near the speed of light. These neutrons go too fast to split the surrounding uranium. Neutrons slow down as they bounce around inside the graphite until they travel slowly enough to split more atoms. The graphite is called the moderator because it moderates the neutron speed. Each graphite block has a hole down the center, which contains the pipes for the fuel channels and control rods. Water flows inside these pipes at high pressure. The uranium fuel is formed into these small pellets. Each pellet is extremely fuel dense and contains the heat energy equal to a truckload of coal. A reactor must have an on-off switch and a way to set the power level. This is done with control rods. These are made of boron, which is a very powerful neutron absorber. When the rods are in the core, they kill the reaction. With about 80% of the rods withdrawn from the core, the reactor runs at full speed. When the control rods were extracted, they left a space behind. The lower half of the control rods were made of graphite, which filled this void. Substituting boron with graphite was a sound design principle. The reactor was more efficient, and it made the control rods twice as effective. The explosion was the result of a design error called the tip effect. This caused a momentary power spike precisely when the control rods were supposed to kill reactivity. The graphite displacers did not extend all the way to the floor of the reactor. The lowest 1.25 meters were cut short to equalize fuel burn. The base of the reactor was where things went badly wrong, but we will come back to this. The objective of the test was to simulate loss of grid power and verify if the flywheel effect of the turbines could power the water pumps until the diesel generators powered up. 3 previous attempts at this test had failed. The test had to be performed during a reactor shutdown, but on this day, the shutdown was paused at 50% power for most of the day. This resulted in two crucial contributors to the disaster. One, the reactor became neutron poisoned, and two, the test was performed by the less experienced night shift, who had not been properly briefed. At 1 a.m. the shutdown began, but was paused because the electrical grid needed additional power, and Chernobyl Unit 4 had to make up the shortfall. After a 19-hour pause, the shutdown was permitted to continue. The new shift took over at midnight and put the reactor onto auto control to keep it steady at 22% power. Except auto mode was not designed for a poisoned core. Power plummeted to 1% before the test had been done. While the reactor was running at half power, it became poisoned with xenon gas, which is a powerful neutron poison. A basic reactor rule is to never restart a reactor which has been poisoned because it is unstable. Xenon forms 6 hours later and interferes with the fine equilibrium of the nuclear reaction. The engineer in charge, Anatoly Dyatlov, was under pressure to do the test. He made the fateful decision to extract almost every control rod to bring the reactor back up to enough power for the test. This was like in a car applying more than full throttle to counter a jammed handbrake. 1 hour after the reactor stalled, the controllers had raised the power back up to 6%. The test was performed at 1:23 a.m. and lasted 40 seconds. The control staff had agreed beforehand, upon completion of the test, the AZ5 button was to be pushed to complete the shutdown. The control staff reported all was calm at this time. You may be familiar with the flip cover and rotating switch, but this was the retrofit after the disaster. The button Leonid Toptanov famously pushed was most likely this one. The control rods were in this configuration when the AZ5 was pushed. It is frightening that there was just one rod fully inserted. At no time should the core have had less than the equivalent of 26 rods active, but on this evening it had almost none, because of the misguided attempt to counterbalance the xenon poison. The reactor had been pushed too far. The AZ5 inserted all the control rods simultaneously. Reactor 4 was teetering on the brink, and the tip effect would be the final straw. Water is a weak neutron poison. As the graphite displaced the water, a temporary power surge formed across the floor of the reactor. The boron would arrive too late. The rapid jump in power caused steam bubbles. Less water meant less neutron poison, more heat, and more reaction. This was the feedback loop to destruction. There was now nothing stopping a reactivity runaway. The base of the reactor was overwhelmed, and fuel channels vaporized. Reactor pressure was lost, and coolant water flashed to steam, increasing reactivity across the core. Reactor 4, in that instance, was producing the energy equivalent to much of the Soviet electric grid. Reactor power surged to an estimated 20 times the maximum. We will never know, because there was nothing left to do the measuring. The reactor drum and the building structure could not hold all that sudden energy release. The explosion blew the 2,000-ton reactor lid through the roof, and it landed back in the reactor pit on its side. The north face of the building fell away in the explosion and exposed the steam tanks and main pumps. Firemen spoke of warming their hands over the graphite, which was lying all around on the ground. They were unaware they were exposing themselves to lethal doses of radiation. This was a heat and gas explosion. It was not an atomic bomb, and nuclear scientists get frustrated when Chernobyl is called one. This is the control room about 25 years later. Its equipment had been reused elsewhere, while the remainder was scavenged by souvenir hunters and radiation stalkers. Soviet nuclear scientists were aware of the tip effect problem. There had been previous channel ruptures from the AZ5 tip effect, in Leningrad 1975 and Ignalina 1983. Design changes had been recommended. The RBMK was considered very robust, and it was widely believed that an RBMK could not explode. No changes were made, and crucially the lurking danger was kept secret from operators. Had they known, they could have compensated for it in their decision-making. The controllers took comfort in the AZ5 emergency shutdown button always being there if they needed to shut down the reactor in a hurry. But it turned out to be the hidden detonator in the wrong configuration. The IAEA Commission states that at below 50% power, the control instruments provided incomplete feedback. The low power dangers were not well described in the operating documentation, and the procedures were sometimes contradictory. The operators would have been somewhat blind to what was going on inside the reactor, and had to rely more on experience and intuition for control. To build inherently safer reactors, later designs, including those in Russia, utilize water as the moderator. Water is a far superior moderator. It added a vital additional automatic reactivity control, and the core could be way smaller. As the water boils into steam, the moderator disappears, and there is an instantaneous drop in reactivity. With higher grade uranium, water can be used as the moderator. Graphite was a favored moderator in earlier reactors around the world for low-grade uranium. The switch to water happened when uranium enrichment technology had advanced to the point where the large quantities required could be produced. With perfect hindsight, it is so easy to be critical of a time when the science was in earlier stages and there was minimal computer modeling. Man can dream up the most amazing things, but ultimately it is humans who are responsible for the things going wrong. We will never really know what happened in the control room that night, and tragically, most who were there paid with their lives, as they heroically scrambled to deal with multiple other dangers that could have put the other reactors at risk of meltdown and a wider disaster. It's natural to focus on the recklessness of a few, but this is as much a story about the epic bravery and personal sacrifice of so many. Occasionally humans fail, but mostly we succeed. Thank you for watching. If you enjoyed this, please add a like and subscribe to my channel to be notified of more videos like this.
So in this also, the technicality and everything is like we should keep it apart. But the human error was that the manpower was inexperienced, right? The manpower was inexperienced. And also, if you have seen the web series on Hotstar, I recommend every one of you to watch this. On day one, so many responses were there that they have watched this web series. But I will recommend to everyone. Right now, we are 46 plus people are there. I am recommending this to everyone that please watch Chernobyl on the Hotstar. You will see that what can these dangers like affect human life, environment, and everything. Right. In this case also, it was a manual error, and in one of her line told by speaker also that it's not plant which creates these hazards or which create these accidents. It's always human. It's always human who are contributing factors in these accidents. Even if it is like design flaws, designs are done by us only, right? So it's always human errors which has caused these disasters. We have seen Piper Alpha, it was human error. We have seen Texas City, it was human error. We have seen this Chernobyl, it was human error. And last but not the least, we will see Bhopal. So many of you might be already aware of this. You might have seen this, and in academics also, people have saw this to you. But still, in Bhopal also, it was a human error, right? So whenever you are working in plant, try to avoid this human error aspect. Correct. If it will be removed, then there will be like a possibility of 99. There is a 99% chances that the plant will run safe. If you will remove this human error from the grassroots. Grassroots means from the design level at the start of only. No, because it is inexperienced, because inexperienced persons are involved. It is not like that we are blaming inexperienced person, but the thing is, as I told you that whenever in Nayara Energy or in SR, during the startup of the plant, I was in my second year, right? In 2014 I joined, and in 2015 there was a shutdown. So when shutdown was there, all the people like me were inside the plant, right? And all the experienced people, including our head of the plant, was working from control system, DCS. Whatever they will tell us, we have to follow that only. We don't have to do any extra step. They will only tell us. Along with us inside the plant, two experienced person will be there, and all of the experienced people will be on control panel only. Because all the plants are automated, the decision will come from top management only. Right. So it is not like we are blaming inexperienced person, but companies should never assign a work to inexperienced person. And you are right that mistake is made by experienced person. But the thing is, experienced person has assigned this. So we are not blaming in a way inexperienced person, but we are blaming company. That company has assigned the work to inexperienced person. So it is a fault of management, not a fault of inexperienced person. Right? When I told in previous videos also that the contributing factor is inexperienced person, but the thing is, it is the main contributing factor is management. That management has assigned this inexperienced person. Right, so it's a fault of management, not directly the inexperienced person, but the management who has deployed inexperienced person for this. Right? Okay, so now we will see Bhopal gas.
People of Bhopal, capital town of Indian state Madhya Pradesh, were sleeping through a cold, intervening night on 2nd and 3rd December 1984. Nothing was out of the ordinary, and the night seemed like any other silent, shivering winter night of the region. But that was only superficial. Somewhere in the eastern part of the city, something nightmarish was happening inside a pesticide plant of the Union Carbide India Limited. An industrial disaster of incomparable magnitude was about to happen. The Union Carbide India Limited plant was established in 1969. 51% was owned by the Union Carbide Corporation and 49% by Indian authorities. The factory used to produce a pesticide which UCIL had branded as 7. A chemical called methyl isocyanate was used for producing this pesticide. Therefore, the factory stored a large amount of MIC inside its premises. On December 2, 1984, it was a routine day at the UCIL factory. MIC was stored in an underground tank. The pipeline washing started at 9:30 p.m. as a routine maintenance operation. Between 10:30 and 11 p.m., workers engaged in the pipeline washing became aware of a leak. However, nothing was done, considering it a normal leak. By 11:30 p.m., workers in the MIC area were feeling the effects of minor exposure to MIC gas and began to look for a leak. One was found by 11:45 p.m. and reported to the MIC supervisor on duty at the time. A decision was made to address the problem after 12:15 a.m. tea break, and in the meantime, employees were instructed to continue looking for leaks. In the 5 minutes after tea break ended at 12:40 a.m., the pressure in the MIC tank rocketed up to 55 psi. Water had begun to leak into the tank E610 containing 42 tons of MIC. The resulting exothermic reaction increased the temperature inside the tank to over 200 degrees Celsius. One worker witnessed a concrete slab above the tank E610 crack. About 12:50 a.m., the emergency relief valve of the tank burst open and large quantities of MIC gas leaked into the atmosphere. The workers at the factory realized the risk of a massive disaster. They tried to activate the safety systems available at the factory at about 12:50 a.m. There were 3 safety systems. First was the vent gas scrubber, which was considered to be the main line of defense. The scrubber was supposed to spray caustic soda on escaping vapors to neutralize the MIC. However, it was not in operational condition. Then, the workers tried turning on the flare tower to burn off the toxic gas. This system was also not in working condition, as a piece of pipeline leading to the tower had been corroded and had not been replaced. The workers then tried transferring the MIC from the tank into a nearby spare tank. The gauge of the spare tank indicated that the tank already contained something. This gauge indicator was found defective later on. After failure in all 3 safety systems, the workers attempted to douse the leaking gas with water spray. The water spray only reached a height of 100 feet from the ground, while the leak was at 120 feet above the ground. At 1 a.m., the workers realized that nothing could be done to stop the leak. Most residents of Bhopal were sleeping when the gas began to leak. Many woke up only because they heard their children coughing or found themselves choking on the fumes. As people jumped up from their beds, they felt their eyes and throat burning. Some choked on their own bile. Others fell to the ground in contortions of pain. As on 3 sides, the UCIL plant was surrounded by slums and other poor settlements, the people living in these colonies were the worst sufferers. There was no warning or guidance to the general public around this time. There were 2 types of alarms in the factory, one mild siren for workers and one loud public siren. The 2 siren systems had been decoupled from one another in 1982 so that it was possible to leave the factory warning sign on while turning off the public one, and this is exactly what was done. The public siren briefly sounded at 12:50 a.m. and was quickly turned off as per company procedure meant to avoid alarming the public around the factory over tiny leaks. The public siren was started only at about 2:30 a.m. Since the gas leaked from a 30-meter chimney, it was not high enough for people to escape the effects. It was not long before the entire city was enveloped by an invisible but extremely toxic gas. People who were cozily lying inside their homes a few minutes ago, they now began to feel suffocation, cough, burning eyes, and vomiting. Streets became crowded with people running here and there for help. The chaos went on throughout the night. Local hospitals were soon overwhelmed with the patients, a crisis further compounded by lack of knowledge of exactly what gas was involved and what its effects were. Within hours, the streets of Bhopal were littered with human corpses and the carcasses of buffaloes, cows, dogs and birds. About 3,000 people died immediately on that night, and another 6,000 died in the next 1 week. Yet another 15 to 20,000 people died over a longer period of time due to the effects of the poisonous gas. Still, about 500,000 people were directly or indirectly affected, with 38,000 temporary partial and roughly 3,900 permanently disabling injuries. Investigations into the tragedy showed that there were many shortcomings at all levels. The UCIL factory used 3 tanks to store 68,000 liters of liquid MIC, and it was to be kept under pressure using inert nitrogen, which helped with the pumping of MIC when needed and also kept impurities at bay. The safety regulations specified that a maximum of 50% of the tank should be used for storage, and the MIC was to be stored at 0 degrees Celsius at all times to keep it inert. But the storage tanks at the UCIL were filled over the specified limit of 50%, and moreover the refrigeration system used to maintain the temperature of liquid MIC was not in working condition since January 1982 due to cost-cutting measure. The MIC was kept at 15 to 20 degrees Celsius instead of the recommended 0 degrees Celsius. In the last days of October 1984, the tank E610 lost its ability to maintain the nitrogen pressure, which halted the production of MIC in the plant. The production was soon started again despite a failed attempt of re-establishment of the system. Moreover, the UCIL factory did not have much information about the safe storage of these highly toxic gases. The medical fraternity did not have the requisite know-how to deal with such kind of contamination and at this scale. There was a lack of coordination between the factory and the emergency services. There were also not many trained professionals in that factory. Cost cutting had also had its impact on the safety of the plant, its employees, and the people living around the plant. The plant was also situated in a densely populated area of the city, which went against most known norms. There have been several theories on the reason for the entry of water into the tank. The workers claim that because of the bad maintenance of leaking valves, it was possible for the water to climb from the point where the pipeline washing was performed to the tank E610, while the Union Carbide said that it was not possible and that it was an act of sabotage by a disgruntled worker who introduced the water directly into the tank, although there has never been any proof of this. The most important factors leading to the mega gas leak were plant design, the economic pressure, and the cutting back on, though there were early warning signs of trouble ahead, signs that were ignored. On December 25, 1981, a leak of phosgene killed one worker at the plant and severely injured 2 others. On January 9, 1982, 25 workers were hospitalized as a result of another leak at the plant. During a safety week proposed by the management to address worker grievances about the Bhopal facility, repeated incidents of such toxic leakage took place, and workers took the opportunity to complain directly to the American management officials present. The Union Carbide sent a team of US experts to conduct a routine safety audit at the Bhopal plant. The report, which was sent to Union Carbide's US management, stated leaking valves, potential for the release of toxic materials, 61 hazards, 30 of which were major, and the 11 of which were in the MIC or phosgene units. However, nothing was done to address the report's suggestions. Instead, remedial measures were then taken at Union Carbide's identical MIC plant in West Virginia, USA, but not in Bhopal. In August 1982, a chemical engineer suffered 30% burns over his body on coming in contact with liquid MIC. Several leaks occurred between 1982 and 1984, which were largely ignored. In the wake of these incidents, workers at the plant demanded hazardous duty pay scales commensurate with the fact that they were required to handle hazardous substances. All of the requests were denied. As a result, it led to the worst industrial disaster of all time. On December 7, 1984, Warren Anderson, the CEO of Union Carbide, was arrested in Bhopal but later released on bail upon a promise to return. In December 1987, the Central Bureau of Investigation filed a charge sheet against Anderson and other accused. In 2003, the Ministry of External Affairs sent a request to the United States for Anderson's extradition. However, this and further requests were turned down. Warren Anderson never returned to India and lived a comfortable life in the Hamptons until his death in 2014. In January 2010, 7 ex-employees, including the former UCIL chairman, were convicted in Bhopal of causing death by negligence and sentenced to 2 years imprisonment and a fine of about $2,000 each. An 8th former employee was also convicted but died before judgment was passed. A compensation of nearly 470 million US dollars was paid by the Union Carbide to the government of India, but legal delays, including identifying the victims, slowed the payout rate to a crawl. The only memorial ever built in Bhopal was privately funded, designed by a daughter of Holocaust victim. In bold letters, the inscription reads, "No Hiroshima, no Bhopal, we want to live." Many years down the road after the Bhopal disaster in 1984, some basic cleanup efforts had taken place, but a lot of contamination is still there. The local people have to live with this environmental pollution every single day. More than 100,000 people are still suffering from the debilitating effects of the gas, which includes respiratory problems, cancer, congenital birth defects, blindness, and many other diseases. Every year since then, scores more are still dying in Bhopal from the various after effects. It has resulted in many children being born with genetic defects, mutations, and mental retardation. It has also had a long-term impact on the reproductive cycle of the affected women and the quality of their breast milk. Besides the effect on people, the impact it has on the environment of that area is also far-reaching. There are still 100 tons of toxic waste alone, which could lead to a continuous poisoning of the soil as well as the groundwater. Some areas in and around the factory are still so polluted that someone entering the area is likely to lose consciousness in less than 10 minutes. In November 1999, international environment watchdog Greenpeace tested soil, groundwater and wells in and around the Union Carbide factory and found 12 volatile organic chemicals and mercury in quantities up to 6 million times higher than expected. While the Bhopal tragedy has certainly received a lot of international attention, not much progress has been achieved to improve people's lives in the area. The tragedy is a burning example of one of the deadliest disasters caused by human negligence in maintenance. I hope I have shed some light on the event and the aftermath of the disaster.
Ethical means, yeah, ethical means it is your right. It is your right. If you are inexperienced, you refuse in the sense you can ask for the some support of experienced person. That if this person will come with me and then I will do this, and if something will happen, it will be not my responsibility. You can always person can say this. Right. If the person is inexperienced, he or she can say this, right? Because ultimately it's about safe practice. What inexperienced person is demanding is it's a kind of safety policy, right? So it is always good to refuse work if you don't know about that, and it is always ask for a help or support from the experienced person, right? So in Bhopal, we have seen that all of the safety measures were not working, right? The tower, curtains, their storage tanks, everything were in like not working, and so it was like the study was not done properly. There were no any alternatives. Even if the plant is nearby to the habitats of people, people were not known about this kind of thing. That what is happening inside the plant, people were not known about this. Also, hospital staff, they were not known about this. If something will happen, what they have to do, right? So, in the history of this safety area of these chemical industries, Bhopal gas tragedy is one of the, say, landmark or remarkable examples. Since then, after Bhopal gas tragedy, there were so many transformation in the rules of this safety and management, right? So many rules were refined, so many things were changed, so many rules came into life. after this Bhopal gas tragedy. And even the environmental aspect, on day one, we have seen that what is the effect of this accident. So environmental aspects, it has shown that even the soil and water, groundwater, and even Supreme Court of India has to intervene in this matter, and Supreme Court of India has to order to Bhopal to provide a good quality water to people. At this level, this was happened that even groundwater was this much contaminated, and Supreme Court of India has to intervene, and they have given order to Madhya Pradesh government to provide a pure and like potable water to people of the Bhopal while living around the area. And image of this company, Union Carbide, in 2001, Union Carbide was sold to Dow. If you will study the petroleum production of petrochemicals, not petroleum production of petrochemicals, the subject, if you will study in this in detail, there are so many patented technology by Union Carbide which are still in use. The company was at that position. Their technology was very robust. The patents and the technology for manufacturing of these petrochemicals, they were very experienced in them. The technology was very robust. Even their processes are used in nowadays also. But due to this incident, the reputation of company went into vain. And the situation came that the company has to sold out to another company. Right. So these many effects came. And even in this Trevor Clays, which the person who has dedicated his life and the link I have said about his books, he used to mention that the material or the chemical which is not part of your process should not be leaked. Now, this methyl isocyanate is not their raw material. It was intermediate. If I can show you the reaction, yeah, this is the reaction. So here, this is your methyl isocyanate. This is intermediate. We have seen that they were manufacturing 7. Now, they could have choose this alternate route of this reaction. This component is not hazardous, right? Here it is written, if reducing inventories or intensification, it is called not practicable and alternative is substitution. That is using a safer material or route. Product was made from phosgene and methylamine and alpha naphthol. Right? They could have used this route as well. But because they have used this way. And methyl isocyanate was intermediate. You should not store intermediate because the meaning it is intermediate. Intermediate will always be reactive. Intermediates are not stable compounds, right? Because that's why they are known as intermediate. You should not store intermediate, and they were they used to store in so much high quantity, right? So these many of steps you should take to avoid this type of hazards, right? This Trevor Clays, this person, please, I will suggest to read his books. He has explained in very good manner these safety aspects, right? So I think that's it from my side for the last day. It was very enjoyable to have and to spend a time with you guys. And so many questions were there from your side, and it is very good that you have took interest. Even if it was a Friday, Saturday, Sunday, you guys came and attended this lecture. So, and like I can trust, and it is good for me as well, that because I was sharing some knowledgeable information, then only you guys came, right? So, like it is good for you as well. It is good for me as well, right? So thank you for coming, and thank you for spending 3 days of 1.5 hour each on every day to share with me, right? Thank you for your time, and thank you for everything. Thanks to Hers and IADP PDPU. Okay, thank you for everything. Thank you for giving me a chance.
Thank you so much, sir. Sir, actually, the entire session and workshop was very good. It was so informative. The knowledge coming from the experience can never be achieved from any textbook. So, with that quote, the things and the tips and the guidance that you have given to us is actually very awesome. No one will come and give this guidance, and we ensure that we will keep all the tips that you have given in our minds and will utilize at the time when we join the company to maintain the safe culture around the plant and around us. So thank you so much, sir. And
Yeah,
I thank
sure,
to
sure.
every participants for joining the webinar or being interactive in the webinar. And actually, it is this sir, Mr. Sagar sir, who kept the webinar interactive. So thank you so much, sir. The content was
Yeah,
really awesome.
yeah. Thank you, thank you.
Thank you, sir. And actually, the session now we are going to conduct a quiz, and the participants will attend the quiz will be provided the certificates of the workshop. Thank you, sir.
Yeah,
And
yeah.
yeah, if the participants want to join the future sessions of IADC PDU student chapter, so the links are shared in the chat box for the platform, social media platform in Instagram and LinkedIn. So you can go through it. Thank you so much, sir, once again. And it was nice to have you with us for 3 days and for
Yeah.
your valuable time. Thank you so much.
Yeah, yeah. Thanks a lot. Thanks a lot. Yeah. And in future also, if I can be able to do it for
Yeah,
you
yeah, sir.
guys,
We
I
look
will.
forward
Yeah,
to have you in
yeah, yeah.
future
I
as
will
well,
be
sir. Definitely.
definitely look into it, and I am always available for the kind of this education spreading and all. So yeah, you can all the time you can contact me, right? Yeah.
Yes, sir. Actually, it's your willingness and the interest of participants who made this event to be happen. So thank you so
Yeah,
much
yeah,
again.
yeah, yeah.